Hello, we're going to work on difference quotients for radical functions. And this gets to be a little bit tricky. There's a really important algebra trick in here. And there's a little piece of this that you're just going to have to remember. Otherwise, once you've got that trick down, it all comes together pretty nicely. So let's just go ahead and work on setup, and I'll tell you when we hit the algebra trick part. Okay, so f of x is the square root of 3x, and we want to find f of x plus k minus f of x over k. So I'm going to break this into some pieces. So piece number one, f of x plus k. F is the function that takes whatever we give it, so we're giving it x plus k, and it multiplies by 3 and takes the square root of the entire thing. And I can even clean that up a little bit by distributing the 3 through. So I'm going to make that the square root of 3x plus 3k. Number two, f of x, that's the original function we were given. Plain old f of x is the square root of 3x. So we are supposed to build this fraction. I'm just going to do that. That's my scratch work. F of x plus k is the square root of 3x plus 3k minus f of x, which is just the square root of 3x, all over k. So we get this, and if you got here, you're understanding your function notation, and that's beautiful. There's an element of this that might seem contrived until you get to calculus, but our goal when we're simplifying difference quotients, and I do want to simplify this one, is to always get to the point where you can cancel this k out, and I'll even give you a little bit of the why. When we get to calculus and we're simplifying difference quotients, our goal is to be able to let the k, or often we use h in that place, equal 0, and we can't let k be 0 if there's that lone k in the bottom. There can be other k's. There could be a k plus 1, that would be fine, but not just a lonely k that makes the denominator 0. So the goal is to do something to manipulate the top of this fraction to the point where we can separate a k out and cancel. But it's really stuck here. There's nothing that we can do as this is written now to try and combine or simplify or do much. So the question becomes, how do we get rid of the square roots in the numerator so that we can start to manipulate the terms that we have up there? And that's not a trivial question. That's actually rather tricky. So this is going to be one of the messier algebra things we do this quarter. I think the messiest is probably rational, but this is right up there. So the goal here, let's see, is to do what we would have done in an algebra class where we would have maybe rationalized a denominator. So if you had something like 1 over square root of 2 and you don't want the square root in the denominator, you'd say, well, I'd like to square it, but squaring a fraction changes its value. So I can't just go squaring fractions. I'll change the number. Instead, what we do is say, well, squaring is the same as multiplying by itself. And we can multiply the denominator of that by 2 as long as we also multiply the numerator by 2. So that gives us the square root of 2 in the top, but in the bottom we get the square root of 2 squared, which is plain old 2. So that's the beginnings of the thinking, but that doesn't even work here because what we really have is something a little bit more like 1 over the square root of 2 plus 1. And if we multiply that by square root of 2, we are doing the right kind of thinking. But what happens is you have to distribute. So you do get the square root of 2 squared, which is 2, but you also get 1 times the square root of 2. And we have not succeeded in eliminating the square root. So we have to be a little trickier when that square root is part of a sum or difference. And what we actually go for is a difference of squares. And we're going to use it backwards. So I'm going to say, one of the facts that we hopefully know, and the place we've used it most is factoring so far, is that if we have a plus b multiplied by a minus b, that turns into an a squared minus b squared. And again, mostly we've been using this backwards, where if we see x squared minus 4, we say, oh, it's a difference of squares. It'll become an x plus 2 times x minus 2. But now we want to do it backwards, because notice, if we start with this top statement, what we end up with has something squared minus something squared. Every piece of that ends up with a square on it, which means if there's any square roots in the a or the b, they'll be gone. So what this is called is multiply by the conjugate. It's like this is our a and this is our b, and we want to multiply by the exact same thing. square root of 3x plus 3k, square root of 3x, but with a plus in the middle. So this will just depend on what the initial sign is. If the initial sign is a plus, we would use a minus in the second half. And if the initial sign is a minus, we'll use a plus, which is what we have here. Okay, so we have to do whatever we do to the top to the bottom, otherwise it won't stay balanced. Remember, the real goal here is to change the way it looks without changing its numerical value. So this fraction has some value. We want to be able to accurately claim that the next thing we write is equal to what we started with. Okay, I'm going to write this all out, and it's going to look awful. Once you get to the point where you can see what's going to happen, you can see this a squared minus b squared coming, you don't have to write every step, but I want you to know where it really comes from. So I will this time. Looking back up here, we are going to FOIL. So we're going to take these first two, and we're going to say if I multiply the square root of 3x plus 3k by itself, that becomes the square root of 3x plus 3k squared, and the squared and the square root eliminate each other. So I'll write that out in case that didn't stick just hearing it. So we get this multiplied by itself, which is the same as squaring it. So that is going to eliminate the square root for us. Squaring and square rooting are inverses, so that will get rid of the square root, which is what we want. This feels a little questionable as we do the outside, because that's not going to eliminate. That's not the square root multiplied by the exact same square root. That's the square root of 3x plus 3k times the square root of 3x, and nothing particularly nice happens there. I'm going to have to make this fit here. Let's go like that. You could mush that into a single square root. You could rewrite that as the square root of 3x times 3x plus 3k. You don't have to, but sometimes it looks a little nicer if you do that. So when you're multiplying, you can combine square roots. This is a plus. Okay, here's what saves the day. When you do the inside, you get that exact same product of the square root of 3x plus 3k multiplied by the square root of 3x, but this time there's a minus sign. So even though that's really ugly and messy, we have one of these, square root of 3x plus 3k times square root of 3x, minus the exact same thing. That adds up to 0. So those two will drop out, they zero out. And all we have now is the last two, which is the square root of 3x times a negative square root of 3x. So there's going to be a minus, and that's the square root of 3x squared. Again, you can do a little bit of skipping some of this stuff that I'm writing down here as you get comfortable. I totally believe if you do it a few times, you'll be able to see how this is going to work out. But until you do feel confident, maybe just write it all out. I would rather have to do a little bit of extra writing and make sense of this so that it sticks with me for longer. Okay, so there's where I'm at. Don't forget that you added one to the bottom as well. So let me just regroup and say what I have on top. I have a 3x plus 3k. The square root is gone. All that middle stuff is gone. And I have a minus 3x. That square root is gone as well. All over k times the square root of 3x plus 3k. Plus the square root of 3x. Okay, and notice something else nice happens. The 3x's actually drop out as well. So now all I'm left with is a 3k on top. And I am almost done. Once you get going on these, they actually fall apart really nicely, but it does take a little while to see what's going on. It looks really bad at first. And now that there's nothing but 3 times k on top, I can cancel. I have to make sure that k is a factor of the top and a factor of the bottom, and it is. That's k times everything in parentheses on the bottom and k times 3 on the top. Remember, when we're doing this kind of canceling, what we're saying is k divided by k is 1. So we're using division to cancel, which only works if it's attached by multiplication. Division and multiplication are inverses, so we've got to have that going. So my final answer here is going to be 3 over the square root of 3x plus 3k plus the square root of 3x. And that's a beautiful answer. It might not look any nicer to you. Like I said, there's a little bit going on here where you won't get the full story until calculus, but we want to get really good at the function notation setup part and the simplification part so that we're only adding a little bit of conceptual stuff when we get to calculus. Thanks for watching.